Hello everyone, my name is Sahar Mazloom from George Mason University, and in my talk, I'm going to show you how we can learn on larger scale data with security and privacy. Every day, we generate a huge amount of data which are mostly sensitive, such as medical or financial records. Service providers look at our data in Clear to run some machine learning algorithms in order to provide some services for us, such as movie recommendations or targeted advertisements. But at the same time, they put our data at the risk of data breach. One of the promising solutions to protect our data that has been around since World War II is using cryptography. But how can we still use and compute on our data while it is encrypted? Secure multi-party computation is a branch of cryptography with the goal of creating methods for parties to jointly compute a function over their inputs, while keeping those inputs private. That function F can be a machine learning algorithm that multiple parties are interested to run on their encrypted data. Matrix factorization is a nice example of a machine learning algorithm that has been extensively used by major companies and content providers as a building block for the recommendation system. In matrix factorization, the goal is to factorize the matrix of ratings as the product of two lower dimensional matrices of users and items. The model is trained by using the gradient descent method, which is a popular optimization algorithm and being used in many ML computations, such as support vector machines, deep learning, and many others. In gradient descent computation, the model parameter will be updated iteratively until a local minima is reached. For instance, in a recommendation system, imagine a rating matrix consists of rating values given by users to different movies. In order to decompose the matrix R into matrices U and V, we should minimize the objective function by computing and updating gradient values of users and movies in each iteration. We looked into machine learning community to understand how these ML algorithms can be trained faster. And we learned that graph parallel computation frameworks, such as MapReduce or PowerGraph, can help us. The idea is cute and simple. If we can model our problem as a graph, then we can solve that problem by applying the following simple operations on the graphs. In the frameworks, the data is assumed to reside in a graph structure, and the result of computation is reached through an iterative process. It's called gas model of operation, which stands for gather, apply, and scatter. At first, the data is gathered from all edges to their neighboring nodes. Then, in apply phase, a computation, which can be computing gradient descent values, is applied on the data at each node. And finally, the processed data is scattered back to the neighboring edges. And then the next iteration starts. There is a work done by Nayak et al. That proposed a secure version of this graph parallel computation framework called GraphSC. Assume all the data in the graph is already encrypted. So in order to preserve the privacy of data, they only need to hide node degree and edge structure of the graph. So in order to do that, they added an extra operation to the framework and called it oblivious sort, which is a secure sorting algorithm. It costs n log square n computations, which is fairly expensive if n is large. Applying a framework to compute matrix factorization on a matrix of size 1 million ratings with 6,000 users and 4,000 movies takes almost 13 hours. And one of the main reasons that they had to use that expensive secure sorting operation is the problem of hiding access pattern. So I'll show you a problem of access pattern with a simple example of counting user inputs, or as we call it, the histogram problem. So here we want to count the number of different elements in a large data set. Imagine users submit their secret shared data to two untrusted non-coding computation servers Let's say one could belong to Amazon, the other could belong to Google. And each user contributes a single input value from three different colors, red, green, and blue. The data can be secret shared between these two computation parties or can be encrypted and input to either one of them because we don't want any of the servers have complete access to the user's data. Then they involve an interactive secure computation protocol, and at the end the output, which is the exact value of the counter for each type, for each color, is going to be a secret share of the counter values, or it could be the encrypted result. If we look closer to the computation, even when we keep the input and the output private, they are either encrypted or secret shared, the computation servers still can learn a lot from the computation while accessing the data. As you can see here, the computation server accessed an array of secret shared, but still through the process they could know what is the counter values for each of those memory cells. So that's the problem of access pattern. There are already some ways to hide the access pattern, but the simplest one is when we want to read or write every single element, we touch all the other elements to hide which one was the target. This solution has linear cost per access, which is very prohibitive if we are dealing with large data. But there is a more interesting and clever solution, which is going to be using ORAM or oblivious RAM, that translates each memory access to multiple accesses that only one of them is a real one. ORAM has its own line of research, and many improvements have been done to reduce its overhead in recent years, but it is still expensive and has poor logarithmic cost per access. And at the end, the last solution is a circuit-based or the tailored solutions similar to graphics. So the primary question we asked was, can we make secure computation algorithms faster if instead of having full security, we allow something small to be learned by the attackers and then prove that what is learned is differentially private? But keep in mind that differential privacy is a separate orthogonal question from secure computation, since they are traditionally two different areas and are concerned with two different problems. Differential privacy is concerned with what is learned from the output, but here, what we care about is what is learned from the computation itself. We were the first to explore the idea of relaxing the security notion in secure computation by allowing some small leakage in the form of access pattern that preserve differential privacy. Since we assume the data is encrypted, to hide the node degree, we only need to create some dummy edges and then just shuffle them to the real ones to hide the graph edge structure. The number of dummy edges is determined by differential privacy parameters epsilon and delta. Our secure shuffling operation takes only n log n computations, which costs a log factor less than oblivious sort. Using this new operation, we designed our own secure graph-level computation framework and called it Uplift graph. So the scenario is that imagine users submit their secret shared data to two untrusted non-colluding computation servers. Uplift graph consists of secure version of shuffle, gather, apply, and scatter operations, can reduce the time of computing matrix factorization on the same input size from 13 hours to 2 hours. And note that both of these frameworks are only secure against honest but curious adversaries. In this follow-up work, we ask this question again: can we do better? Can we improve the performance of secure computations even further? Several results in secure computation have recently minimized the communication cost by restricting the number of computing servers to 3 or 4 servers, assuming security with honest majority. And when representing the computation as an arithmetic circuit over a ring, as we do here, the cheapest of these results by Gordon et al. Requires sending only 1.5 ring elements per party per circuit gate. So, by leveraging the results of low communication MPC and the security relaxation from our previous work that allows the computation servers to learn some differentially private liquid about inputs, We were able to construct an implicit protocol that can improve the same computation of matrix factorization even further to less than 25 seconds. This protocol can also perform on larger scale data. For example, we can compute matrix factorization problem on matrices with 20 million ratings in less than 6 minutes, or even compute histograms or counting on 300 million users, like what they compute in census data gathering, in almost 4 minutes. To achieve these results, inspired by Gordon et al. And using 4 computation servers instead of 2, we could design a linear Uplift shuffle instead of a quasi-linear one, and we replaced the Boolean circuit with a fixed-point arithmetic circuit to compute, for example, gradient descent values easier. In addition, we made our scheme secure against one active adversary as compared to the previous schemes that would only support semi-honest adversaries. However, merging these constructions wasn't like plug and play, and it has its own challenges. For example, to preserve the privacy of users' data, the party that was responsible to access data shouldn't learn the shuffling pattern. So to solve that issue, we had to partition these tasks between 2 groups of parties. The first group is doing the shuffling, while the other group is accessing the data. We will see that in the next few slides. Another challenge was protecting the scheme against an active adversary, and for that, we had to be able to detect the malicious behavior by verifying the result of each operation at each step. So imagine we have 4 parties, Alice and Bob, Charlotte and David. Every operation done by one group is being verified by the other group to detect malicious behaviors and cheating behavior. For example, Alice and Bob perform an Uplift shuffle. Charlotte and David will verify the correctness of that operation. The same verification happens for gather and scatter, but the apply is different. The apply phase, which is computing the main functionality, should be handled by all 4 parties, and then they all help to verify its results by using a cross-check validation step. So our new design framework has reduced the cost of Uplift shuffle operation by 230 times and Uplift apply by 880 times as compared to the previous work Uplift graph. And finally, one of the other interesting challenges we faced was doing arithmetic operations on fixed point numbers. Doing addition on fixed point numbers is quite easy. Our challenge was when we were trying to compute multiplication on decimal numbers, which requires truncation. And let's see how truncation became a challenge for us. During the apply phase in our scheme, each group computes on their mask data locally and then do a cross-check validation to compare their results to make sure nobody acted maliciously during the computation. If the results don't match, they abort. But since in our computation we are dealing with decimal numbers to compute gradient descent, for example, in some occasions, the computation may result in different truncated values, and the cross-check validation will fail, and the parties consequently will abort, but not because of malicious behavior, only because of mathematical error. So we found a way to handle the truncation error securely without any additional overhead, and we discussed the details of that in the paper. We implemented our framework and ran it on different input sizes for histogram and matrix factorization problems. The differential privacy parameters are set to epsilon 0.3 and delta to be 2 to the negative 40. To recap on the results, our framework can securely compute histograms over 300 million users in about 4 minutes and compute sparse matrix factorization on 20 million records in less than 6 minutes. And here is the comparison of its running time with the previous solutions on the same dataset and the same problem. To conclude, the goal of this work was to show how we can learn on larger scale data with security and privacy. We designed a privacy-preserving machine learning framework that was secure against one malicious adversary, and we used differential privacy to improve the efficiency of our framework. Thank you very much for your attention, and feel free to contact me for your questions. Thanks.